Yeah, very good morning. Now, today's topic is strain. So, what is meant by strain? So, strain is nothing but, so simply the definition is when a force is applied, when a force is applied on a member, there will be a chance of, there will be a chance of change in size or shape is called strain. Is it okay? So when there is a force is applied in a member, there will be a chance of change in size or shape is called strain. So in previous class, I explained that stress is nothing but internal resisting force per unit area. So for developing stress, there should be two considerations. The first consideration is the body should be constrained, and second consideration should be there is a net unbalanced force. So there is a special case is there when the heat is applied. When the heat is applied, the body is freely expands or contracts. So when the body is cooled down, the body is freely contract, means the dimension is decreases, the shape is decreases. When the heat is applied to the member is expanded freely. So in previous case, the first case and second case, there is a force is applied. When you are constrained and applied force, there will be a stress is generated because of internal resistance force. And the second case, when the body is net unbalanced, due to unbalanced, the balancing of remaining force, there will be a resisting force is developed. So that we called as a stress, or unit area is called stress. So in strain also, for change in shape or change in dimension, force is always not needed. Sometimes without force also, there will be a change of shape in shape or dimension, shape or size. So the example is a heat. So when you're applying the heat, so now I'm explaining the three cases. The first case and second case with respect to forces, and the third case with respect to the heat. So I'm taking a member like this. So this is taking a member, a bar. So here also I'm taking a member like this, like a cube. So initially it's having some distance L. Okay, I'm taking this as a 5 centimeters. Okay, this is length. So when this member is constrained, so when this member is constrained here it is placed on the surface. So here also I'm taking a cube like this. Is it clear? So I'm drawing a three-dimensional diagram. So it is placed in some surface or something. Okay. So in this case, this is a axis of this member. So when I applying the axial load, a P on here, so along the axis, if you apply the load, that is called as a normal load. Is it clear? So what happened when you are trying to apply the load? This is a tensile load pulling. So what happened? This bar may be expands like this. Means the diameter is decreases and length will be increases. So initially this is the original length LO. So then this is the final length LF. So initially this thicker line is the original diameter DO. This is the dotted line between the thicker lines. This is the final diameter DF. So what you observe from here, when you apply the force on this member, so there is a change in a dimension and no change in shape. Am I right? Now coming for this case. So when applying the force on this member F, so that force we called as a tangential force. So tangential force is nothing but the force applied parallel to the surface area is called tangential force. The force applied perpendicular to the this area, this is a perpendicular to the area, that we called as a normal force or normal load. So when you are applying this tangential force on this member, what happened? It's maybe like changing its shape. So likewise, so applying means that is a sliding. So after you calculate this length, the length will not change since the length is the same before applying the load and after applying the load. This is the original length. So this is a final length. So even you applying the tangential force, the dimension is not changing, but there is a change in the shape with respect to angle. So what observation made here? There is no change in dimension, but there is a change in shape. So coming from case 3, when you are applying the heat to this body, so what happened? Since the body is not constrained, but simply it is a place on a floor for a stable condition. So what happened? This is the x direction, this is a y direction, this is a z direction. So what happened in the in the y direction and x direction and z direction also, the body is changes its dimension. So whenever you are applying the heat, definitely a body should be some deformation in a respective direction. Means the respective direction means if you are constrained in x direction, there is no change in dimension x direction. If you are constrained like this, for example, this is a body. If you are constrained in x direction, since you are applying heat, so x direction, no change in dimension, but y direction and z direction, there is a dimension change. So in which dimension you are constrained, that particular dimension, there is no change in deformation, means there is no expansion takes place, there is no body, there is no movement of body. So when there is a constraint means there is a stress will be developed. So all these we discussed in the previous class. So now our topic is only simply called as strain. So I'm taking this third case. So when you're applying the heat to this body, so definitely the body will be free to expand or free to move. Means there is a change in dimension or change in shape. So whatever it may be. So the shape, some materials may be changes its shape due to heating. Some materials may be changes its dimension due to heating. Some materials happening both the cases. So it's physically happening both. It maybe changes dimension as well as the shape. So what you observe here? So there will be a change in dimension here. There will be a change in shape here. There will be a change in dimension as well as a shape. So our conclusion is that the change in shape or change in dimension, simply we called as a deformation. So when the deformation takes place, so initially it's having some initial dimensions, having some lateral dimension as well as some linear dimension, means some length is there, some diameter is there. So definitely in some cases, so in the first case, there will be a increase in length. So increase in length, decrease in the diameter. So the deformation is nothing but, so the deformation we can explain as a strain. So as a mathematical expression, strain can be denoted as small e. So the strain can be expressed as change in dimension by original dimension. In the first case, I am taking the case 1 example. So example of case 1. So change in dimension. So there is a two directional changes is there. So change in dimension, length is changes and dimension or diameter also changes. So the change in dimension is a two types. So since the change in dimension is two types. One, change in length. So there is a change in length. There is a change in diameter. So strain can be, we can write as a, with respect to dimension, with respect to length. So with respect to length, the strain is change in length by original length. So change in length is nothing but, so this is a change in length. So this much is a change in length that we called as a delta L, or simply sometimes change in length delta L or delta L, whatever it is clear. So delta L by original length. With respect to diameter also, there is a change in dimension, that is a change in dimension with respect to diameter. So there is a change in diameter to original diameter, that is called change in diameter to original diameter. So simply we called as a strain. So strain, many students think that and they confuse like strain is nothing but a change in length by original length. It's not right. It's not a correct way of explanation of meaning of a strain. So strain is nothing but there will be a deformation, change in shape or change in dimension is called a strain. So the ratio of change in dimension to original dimension is called a strain. So the dimension is changes in the two directions. One is the lateral direction. In the lateral direction we call it as a diameter, and the linear direction we have the length. So there is a change in length as well as there is a change in the diameter. So that's why the strain is equal to change with respect to length, change in length by original length, delta L by LO. And with respect to diameter, change in diameter by original diameter, delta D by D. So both have a delta L is a as a units of some meters or millimeters, and original length also some meters or millimeters. So strain has a no units. It has a no units. Strain has no units. So from case 1, I am explaining. So here you are applying the normal load. So the normal stress or normal force. So the normal force may be the normal strain. So whenever you are applying the normal load, there will be a normal. So due to normal force, there will be a normal stress and normal strain. So due to this normal strain results, this normal strain results either positive or negative. This means your applied load, is, if you apply the load, if you are, for example, this is a member, if you apply the tensile, so what happened? This is a tensile. So the tensile force is gives positive strain. The compressive force leads to negative strain, negative in the strain. Is it clear? So when you apply, tensile force, so when you apply normal force, how many types? Tensile or compressive. So for this member, this is a pulling, this is a tensile force. For this member, this is pushing, this is a compressive. Is it clear? So for this, when the tensile force is applied, final length is greater than original length. When the compressive force is applied, what happened? Final length will be less than the original length. And so what about the diameter? The original diameter is less than the final diameter, and you apply the pushing. So compression means the diameter is decreases. The final diameter is less than original diameter. So strain can be, for tensile force, strain is equal to change in length delta L by original length LO. So change in length we can write as a final length minus original length by original length. So when you apply tensile force, what happened? So LF is greater than the LO. So the net effect will be positive. So when you apply the compressive force, E is equal to delta L by original. So delta L is always nothing but final minus initial or original. So when you apply the compressive force, the final length is less than the original length. This means here we are getting a negative strain. Is it clear? So the normal force is maybe tensile or compressive. When you are applying the tensile normal force, the strain will be positive. When you apply the compressive force, normal compressive force, the result will be negative strain. Is it clear? So till now I'm not so this is a third case. Is it clear? So coming for third case, I'm explaining deeply. So I'm explaining for case 3. So the this is a case 1. This is an explanation for case 1. This is entirely case 1. So this is case 1. So I'm going for case 2. Case 2. So case 2, what you made the observation, there is a change in the shape, but there is no change in the dimension. Is it clear? So initially, so I'm taking about this tangential forces. I'm talking about tangential forces. So initially, this is a 90 degree. So when you apply the force on this member, what happened? So this is a initial member. So what happened? This is a changes like this. Is it clear? So this is called phi. I am talking, this is a phi. This is called change in a shape. Change in the shape. So I'm writing this as a alpha. Is it clear? So I'm talking about this is alpha. So therefore change in angle. So how much the angle is changes is equal to the change in angle is called phi here is equal to 90 minus alpha. Am I right? So initially this is 90. 90 minus alpha is called. So this is a 90 entire this is 90 minus alpha. This is we are getting. Is it clear? 90 minus alpha is equal to change in angle phi is equal to 90 minus alpha that we called as a phi. Is it clear? So this is called change in angle. Is it clear? So this change in angle we called as a simply. So this change in shape or change in angle we called as a strain, simply strain. So the strain in the shear strain, so in the normal strain we denoted as a E, normal strain, shear strain. So this is called shear strain, shear strain. So when your force is applied tangentially, this is called shearing. That is called shearing. This is called shearing. These are shear off. So this is called shear strain. So this is in the case one, that is called normal strain. This is a normal strain. Case one. This is our case one. So our case two is a shear strain. So the shear strain we called as a phi. Normal strain we can denote as a E. Is it clear? So the shear strain phi is equal to, so we can denote it as a phi. So that is always we can measure as a radians. So how we can convert into degrees too? So this is a called degree. This is some angle. This is some angle in degrees. Okay, some degrees. So angle we can made a degree. But always in strength of materials, the change in shape, the shear strains always we have to measure in the radians. The conversion, how we convert conversion from degree to radian. How degree to radian? For example, I am taking this is a member. So initially this is a 90 degree. So when applying the force, applying the force, so it changes like this. So this is a 89 degree. So the change in angle I called as a 1 degree. So from this equation, from the Q equation, phi is equal to strain, shear strain is equal to 90 minus alpha. The alpha is a 89 degree. So 90 minus 89. So the phi is equal to 1 degree. So for degree to radian, 1 degree is equal to pi by 180 radians. So the phi is equal to pi by 180 radians. So this we have this way we have to conversion from degrees to radians. Okay. Nature of strains. Nature of shear strain. So in previous we discussed about the nature of normal strain. So the normal force leads to normal stress as well as normal strain. The nature of normal strain may be tensile or compressive, that may be positive or negative. In the likewise, the shear strains have also, there is a two natures. The first one is a positive as well as a negative. For example, when you are applying the force, this is alpha. So this is a phi. So what we made here, alpha is less than 90 degrees. When the alpha is less than 90 degrees, the shear strain is positive. Okay. For example, if you apply the force like this, is it clear? So this is alpha here. So if the alpha is greater than 90, the shear strain will be negative. So this is the nature of shear strain. So from normal strain, we can introduce a new term. So I'm talking about a normal strain. So this is a member like this. So I'm constrained here. So initially this is a length LO, original length, or initial length Li. So this is a initial diameter, original diameter DO. So when apply, so I'm talking about the normal strain. I'm applying normal force. This is a normal force. So the normal force leads to normal strain. So what happened? This may be decrease its diameter and increase. So this is our final length. So this is a delta L. So this is our final diameter. So from any three dimension, this is x-axis, this is y-axis, this is z-axis. Is it clear? So this x-axis we called as a linear axis. This or a lateral axis. So when applying the normal force, so you can observe that there is a change in the x direction, there is a change in the y direction. Means in x direction length will be there. So x direction, this is a length. In y direction there is a diameter. So in x direction length is there, y direction diameter is there. Is it clear? So when you apply this normal force, so there is a change in dimension in a linear axis, there is a change in dimension in a lateral axis. So there is a change in, so due to normal force, there is a change in lateral dimension, that is called diameter, and linear dimension, that is called length. So our new term is ratio of lateral dimension to linear dimension is called Poisson's ratio. So Poisson is a scientist name. So the Poisson is observed one thing when applying the normal force on any bar, any member. So what Poisson is observed? So when a force is applied on the member, a normal force is applied. So there is a change in a lateral dimension and a linear dimension also. So that ratio we called as a Poisson's. So there is some new term that is called Poisson's ratio, mu. So we can denote as a mu. So some textbooks mu is they can denote a mu or nu or 1 by m. This is a mu or nu or 1 by n, 1 by m. So mu is equal to the ratio of lateral dimension to original dimension is called Poisson's ratio. Is it clear? So the lateral dimension. So from this diagram, so this linear axis we called as a primary axis. This lateral axis we called as a secondary axis. So our length is always our primary motor. That's why this is a primary axis lengthwise. In a lateral wise, that is a secondary motor. So lateral dimension by original dimension. Sorry, lateral strain by mu is equal to lateral strain by linear strain. So lateral dimension is always secondary dimension. That's why we can write as a secondary strain. So linear dimension is always on a longitudinal axis or linear axis, that is called primary axis, that is called primary strain. So mu is equal to lateral strain by linear strain or secondary strain by primary strain. So Poisson ratio is equal to ratio of lateral dimension to ratio of linear dimension. So the change in linear or lateral dimension we call it as a strain. So simply we call it as a Poisson's ratio is a lateral strain by linear strain. So this is we can write as a not dimension, strain, linear strain. Is it clear? So lateral strain, in lateral strain we called as a secondary strain. So the dimension is a lateral strain or linear strain. So strain in lateral secondary strain, change in lateral is called diameter, change in length by original diameter. Then linear strain in x direction always, that is equal to primary strain. So change in length by original length. Is it clear? Therefore, Poisson's ratio is lateral strain by linear strain. Is it clear? This is our Poisson's ratio. So Poisson's ratio about natures. So how many natures? Positive or negative? So I will explain. So I'm talking about a sensor. I'm taking normal strain. So two different cases. So here I'm talking about a tensile force. So one side I'm talking about tensile force, since both are in the normal, and another side I'm talking about a compressive force. Is it clear? So I'm taking two different cases. So this is all the I'm taking two different bars. Okay, so initially it having original length L. This is also original length L, original diameter DO. This is also original diameter DO. Is it clear? So since I am constraining here both sides, so in the tensile force, this is a normal tensile force P. So this is a compressive force I'm applying. So what you observe here, so when you apply the tensile force, when you apply tensile force, so what observation we have made? L is increases, length is increases. Am I right? So when the force is applied, the length is increases, diameter will be decreases. We know that all these cases. So length increase and decrease. So in compressive force, the length when you are applying the compressive force. So this is a compressive force. What happened? The length will be decreases. L is decrease and D will increase. Diameter, lateral dimension increases and linear dimension decreases. So therefore, original length is equal to LO. Here also original length is equal to LO. Original diameter is equal to DO. Here also original diameter is equal to DO and final length LF. Here also final length LF and final diameter DF. Here also final diameter DF. So what is change in length? Final length minus original length. So here the final length is increases. So in the tensile force, LF is more compared to here when the tensile force LF is greater than LO, then DF is less than DO. When compressive force LF is less than LO, DF is greater than DO. Is it clear? So final length will be higher than the original length. So the delta L is a positive. So delta D is the final diameter minus original diameter. So the final diameter is less than original diameter. Then it is a negative. From the compressive force side, change in length is equal to final length minus original length. The final length is less than original length. Then it is a negative. Then change in dimension, change in diameter. Again, final diameter minus original diameter. The final diameter is greater than original diameter and compressive force applied. This is a positive. So we can write that Poisson's ratio is equal to lateral strain by linear strain. Simply we called as a secondary strain by primary strain. Likewise here also lateral strain by linear strain. So lateral strain is a lengthwise strain. Sorry, lateral strain is a diametral strain. Linear strain is a length strain. So lateral strain is equal to change in length by original length. In a linear direction there is a length. Change in length by original length. So delta D is the negative. So for keeping both positive, we use here negative. So coming to here, because delta L by L is a positive, but delta D by D is a negative. So for keeping positive Poisson's ratio, we use the negative symbol at the before the lateral strain. So here lateral strain. So lateral strain is the change in diameter by original diameter, change in length by original length. So which one is negative here? Change in length is negative. So here negative symbol is here. So finally mu is equal to minus of delta D by D divided by delta L by L, or mu is equal to minus of delta D by D divided by delta L by L. So this is called Poisson's ratio. So in further classes deeply we can learn about the Poisson's ratio and their effect and their phenomena. Is it clear? So our next class, we can go for Young's modulus and stress strain diagram for different materials. What is a stress strain diagram? What is Young's modulus? And we will first we'll talk about the in next class we'll talk about the Hooke's law. So what is Hooke's law? State that from Hooke's law, what material property we can take, and what are the different types of material properties, and what are the physical meanings of the material properties, and for that Hooke's law, which diagrams we can make, which diagrams we can make, diagrams we called as a stress strain diagram. So stress strain diagram on different materials, so we can learn for the next class.